Hello everyone and welcome to solutions video for round 754 division 2. It went pretty well. I was able to get a good rank and check off my bucket list of defeating people. So yeah, momentarily it's not final, but yeah. So problem A. So what problem A said was we have three numbers A1, A2, A3 and we want to minimize A1 plus A3 minus 2A2. So let's say what I can do is I can choose two numbers and increase one of them by 1 and decrease the other by 1. So let's say I choose A1 and A3. This increases by 1, this decreases by 1. They cancel out, right? Or what I can do is this decrease by 1, this increase by 1. They cancel out anyways. So we have to choose one of the number to be A2. Okay. Now we don't necessarily have to do the operation, but if we do the operation, one of them needs to be A2 to have an actual effect. Now, so I have A1, A3. So let's say I increase it by x. X can be negative. I increase it by y. And x plus y is total, let's say p. So what happens is A1 plus A3 plus p minus 2 times A2 minus p. Now p can be negative or positive, doesn't matter. So it becomes A1 plus A3 minus 2A2 minus 3p. Or I can write it plus 3p because p can be a whatever constant I want. So so this is the final expression. Now I want to minimize this. Now notice that if this is already 0, right? Or then if it's already 0, then I want just p to be 0. If it is 3, however, then I can put p equals to minus 1 and get it to 0. So if it is or like any multiple of 3, so if this value, let's call this k, right? So if this value is a multiple of 3, right? If this is a multiple of 3, then I can get it to 0. However, let's say it's not a multiple of 3. Let's say it is like let's say it is 7. Okay, that is modulus is 2. In that case, what I can do is first of all keep removing threes and get it to like 2, right? So we got it to 2. Just like if I had value 6, right? So this was, let's say this was 8. Okay, modulus is 2. So if a value was 6, we choose p equals to minus 2 and get it to 0. If it is 8, we can get it to 2, right? Then what I can do is remove 3. Yes, so remove 3 again. Okay, sorry. So we remove 3 again and this becomes negative 1, right? And this is the minimum value we can get. Now we have to take the absolute, so this goes to 1, right? We cannot get it to 0, but we got to 1, so this is good. Now in case of in case that it is modulo 1, okay, so like let's say it's 7, and then we take it to 1, and then then what we can do is nothing. We are already at 1, so we have the answer. So the solution is obviously if k is divisible by 3, answer is 0, otherwise it is 1 in both cases. Okay, I did it a little bit differently. I did the same thing. It is related to 3, but it's somewhat weird. It took me 25 minutes. I was doing really bad. So if you did it faster than me, congratulations. You are nothing. You get nothing for that except curse. Okay, so problem B. So in this problem, okay, this was simpler in my opinion. In my opinion, everything was simpler than A. So we have a binary string. Okay, So we have a binary string, and what we want to do is we want to convert it into a increasing sequence or non-decreasing, not strictly increasing sequence, just increasing sequence. So something like this. Okay, so to do this, what we are allowed to do is take a subsequence of the current string and then reverse it. So let's say I take 1 and 0 and then I reverse the string, which is basically like swapping, right? So I get 0 0 0 0 whatever it was and 1 here. So I did it good. Now what we want to do is, well, we wanna so we want to do minimum number of operations, and yeah, so we want to do minimum number of operations and sort it. Now as you can see, at an elementary level this operation is like swapping, right? If it shows something like this and this, right, then this would get swapped by this and this would get swapped by that. So at an elementary level this is like swapping, and also the subsequence we are allowed to take is only decreasing sequence allowed. Okay, so let's have a look at the final state of the string. 1 2 3 4 5 6 1 2 3 4 5 6 1 2 3 4 4 5 6. Let's add one more 1. 1 2 3 4 5 6 7. Okay, this is the final state, right? And what you can see is, among these first 6 numbers, if there is 1 we want to move it away, and among the last 7 numbers, which is n minus 6, if there is a 0 we want to move it away. And the great thing is, obviously, if there are k ones in this range, then k zeros will also be in that range because they are basically replacing each other. So we can just choose the ones that come in the first 6 elements, in the first 6 indices, and the zeros that come in the last 7 indices. And how did I get 6? 6 is just frequency of 0 and 7 is just frequency of 1. So let's have a look at the implementation. Let's copy it into VS Code because light theme. Also Gruffbox is the best. So I take the input, right, and then I store the frequency of 0 and 1 using a map. A little bit more constant factor, but no one cares. Now x is the number of times 0 occurs. So for those, whenever it is not 0 or it is equals to 1, I put it into the answer. And then for the remaining ones, if there is a 0 instead of 1, we put it into the answer. And yeah, as you can notice, we can always do it in only one operation. So the number of operations will always be 1, and then we just print the size of the subsequence we are choosing and the subsequence. And if it was 0, right, then we didn't need to do it, obviously. So that's why I return with printing 0. Okay, so yeah, this was a pretty simple problem. Now dominant character. Now here what we are asked is, we have a string that only consists of A, B and C. Okay, so what we have to do is find the smallest substring such that frequency of A is greater than frequency of B and frequency of A is also greater than frequency of C. Now here, remember, so let's say it's something like this. Okay, imagine all the positions where A is at. Okay, now take any 2 consecutive A's and we can figure out if taking this is beneficial or not in our final substring. How? First of all, if there is no space between them, okay, if they're contiguous, then this satisfies and this will be the answer. Okay, however, let's say there was one space between them. If there was one space, then doesn't matter, it can be either B or C. This condition will satisfy, so this is also good. Now let's say we have two space. For two space, I will do it, but before that, let's have a look at three space. Whenever we have three space, you can see that it would be either all B, or one of them would be C, or two of them would be C. But in any case, either FB is 2 or FC is 2, which which makes this not valid, and so this substring wouldn't be valid. Hence, taking this is only doing harm to us. So taking 3 or more, because when the gap is more, then it gets even worse, right? So taking a gap of 3 or more is always bad. So yeah, forget this. So the answer would always come between A, 0 gaps, 1 gap, or 2 gap, right? Not exactly, because we haven't actually analyzed this case. Now in this case, if both are B, then we cannot do it. Similarly, if both are C, we cannot do it. However, these two cases work, right? Because both are 1, which is less than 2. So for 0 space, this works. I mean, it always works, right? It's always a valid substring. For space of 1, it is always a valid substring. For space of 2, these are valid substring, but these are not. For space of 3 or more, it is never a valid substring. Now, who said that they can only be 2 A's, right? We can have something like this, right? For now, we were only analyzing this part of any final thing that can be like this, and what we noticed is that if the spaces is greater than equal to 3, then that cannot be in the answer, because it always does harm to us. And these are already done, right? B or C, so they also do not come in the length of 3. These, however, come in the length of 3, right? So now obviously, if there is a like this, then it is covered in this situation, so we are not gonna cover that, and that is more optimal as well. If there is a space A, this is also covered, right? If there are 3 spaces A or more, then we don't want to take it, right? If there are 2 spaces and it is like B and C, then this is covered here. So what is remaining? Either both are B or both are C. If both are B, then we cannot do it, but if both are C, we can do, and similarly we can do it this. So these are the all possible situations, all possible substrings, and we want to check them in the order of their size. So first of all, we check this, then these, then this, then this, then this, and then this. This is what I did. Yeah, so because all you had to realize was, for 3 or greater than 3 spaces, taking them is always bad. So you can do a case-based analysis for 0 space, 1 space, 2 space, and you will get this. Or you can actually try to test your luck, and in these type of situations, like when you notice, right, that okay, there cannot be more than 3 spaces, and probably like there won't be too much of these, there probably won't be anything like that. In that case, what you can do is check all substrings till length 100 or something, that may work, or 50. But yeah, these are the find all substrings. I'm not sure if this is the intended solution, but it was a pretty okay-ish case-based question and problem. Sorry, Redbush. And if you look at this, okay, I was just kidding. Okay, no dislikes. So this is my solution. Take the input. These are all the strings I want to check. Make sure to check them in this order. And then for every string X, we want to check if S contains it. If it contains it, I just print the size and return. Otherwise, -1. Okay. Now the last problem, tree labeling that I was able to solve. It's not the actual final problem. So what is this problem? This problem was pretty nice. In this problem, what we said is there is a tree. Okay. So there is a tree, and all of them have numbers from 1 to n. So these nodes are numbered from 1 to n. Okay. And now what there's a game that happens. The first player puts what do they put? Yeah, a token. So the first player puts a token, let's say t here. Okay, let's say it was like 1 2 3 4 5 6 7 8 9 10. Okay, so okay, for the sake of this example, I'm gonna do it like this. Okay, now what happens is first of all, player A puts the token here, then player B can move the token to any adjacent vertex. If so, let's say we are moving from U to V, then what we want is U XOR V to be less than equals to minimum U comma V. So let's first of all, let's analyze what this means. So if we have two values, right, I'm writing the binary representation. Okay, let's do something like, okay, and then when we XOR them, as you can see, if the most significant bit among these two occurs only once, then the XOR would have that most significant bit, and then this would not satisfy. However, if MSB, there is eraser. However, if this was the MSB for this as well, then they become 0, and whatever happens here doesn't matter, because you know this is greater than this same number of digits. Okay, so what we want is for to be able to go from U to V, the most significant bit of U has to be the same as most significant bit of V. So from 1 we cannot go anywhere, from 2 we can go to 3, from 2 we can go to 3, or 3 from 2. We can move among 4 5 6 7. We can move among 8 to 15, among 16 to 31, 32 to 63. So that's the trend. And now what we are asked is we want to rearrange the numbers. So the tree remains like this. We just rearrange the values of the nodes, and what we want is to maximize the starting positions that guarantee a win for player 1. So what kind of places guarantee a win for player 1? Well, if you see, so the first move is placing the token, the second move is moving to some place, right? If we couldn't move there, then obviously player 1 wins, because player 1 places it and player 2 cannot move. However, if there was one place to go, then player 2 will move and player 1 won't be able to move. However, if it is like this, then player 1 will move and player 2 won't be able to move. So what you can see is the length of this path that we eventually take, right? That token goes from here to here to here. If this is even, then player 1 wins, otherwise player 2 wins. But if you want to guarantee for player 1 to win, then what we want is all the paths, right? So all the paths that goes from this needs to be of even length. Needs to be of even length. 4. Only then player 1 will be guaranteed to win, and these are the type of nodes we want to maximize. Also, the nodes which are not connected to anything, or I mean from where we cannot go anywhere, are also winnable, right? Are also guaranteed to win, because player A would place, player 2 would not be able to make a move. So let's erase this because we have already been through this and this. Now, so let's check if we can, somehow place all the numbers such that every number, from every number we cannot make even a single move. Okay, because if that is possible, then there cannot be a better answer than that, because in that case all the nodes are absolute win for player A. So let's do a little bit. Okay, okay, so where was I? Yeah, so let's see if we can do it such that all the nodes are such that player A wins, and that happens only when from node any node U we cannot move anywhere. Okay, for all nodes to be winnable, absolutely winnable, I mean, what we want is this to not be able, from here we should not be able to go anywhere. So what that means is if we are at, let's say, 6, okay, then whatever its adjacent values are, they should not be 4, 5 or 7. Similarly, for 10, 8, 9, 11, 12, 13, 14, 15 should not be adjacent to it. And if you think you know where this is going, you are absolutely right, because now let's have a look at what bar partite is. So if we do a bar partite coloring, right, this is red, this level is blue, this level is red, this level is blue, right? So how many vertices I have in red? 1. Okay, let's use red color. 1, 2, 3, 4, 5, and in blue I have 1, 2, 3, 4, 5. Okay, this was even by chance. Let's actually rig this. Okay, let's add 11 and 12. So these will be blue. So now the number of vertices in red is 5, number of vertices in blue is 7, right? And what we want is, we wanna put these values among these red or blue vertices such that if the color of 4 is red, then all of them should be red, right? Because if all of them are red, then they are never adjacent. Similarly in this, if 8 is blue, then all of them should also be blue. So how can we do this? Let's take the smaller one. Okay, 5. Can we always perfectly fill it, right? If we can perfectly fill this one, then obviously we can perfectly fill that one, right? So let's take the smaller one. Can we perfectly fill this? If we write it, and obviously we can, right? How we do that? See, we have sets of size 1, 2, 4, 8, 16, 32, and yeah, and if you know the basic coin change problem, right, then you know that greedy will work. Why greedy will work? Because it is very common. If you're actually looking at D, then you should know, but let's go over it again. So what I mean by greedy is, we will greedily choose. Let's say its size is 5, right? So we'll choose the set with maximum size less than equal to this, which is this. So first of all we'll put them, and then we'll put 1. Why this works? Because if we put, so let's say we put set of size x into this, right, but the next value is 2x, right, but 2x is also less than 5, right, then we can also put, then we can instead put 2x and then put the other ones. And why this works is because number system, 5 can be represented as a binary number, right? 1, 2, 4, yeah. So this is the binary representation of 5, right, which is 2 to the power 0, 2 to the power 2. So we can take two unique powers of 2 and add them to get this number, right? This is also a reason why we can do it. So whichever way seems easier for you. So what we have to do is, now obvious, we take the set which has size less than the greatest set which has size less than equal to nr, and then what we do is we put these numbers, these values, into the vertices of this set. Okay, so I put 4 here. Let me use a better color. Yes, yellow. This sucks. 5, 4, 5, 6, 7, and then the remaining size is 1, so I put 1 here, and then I can put all the remaining values into the remaining vertices. And yeah, that is the solution. Why it is optimal? Because we are able to always do permutate such that all the nodes are always winnable. So yeah, this game is rigged. Okay, so let's have a look at the implementation. So first of all, what I'm doing is taking the input here, right? And then I have the two sets, right? So red and blue, I am calling them odd and even based on their distance from the root. Now what's happening here is, in this odd and even, I'm storing which vertex. So there are two things, right? The vertex number and the vertex value. Initially vertex value is equals to the number. Now I'm storing what is the vertex number for the odd set and the even set, the red set or blue set. Okay, and how am I getting that? Using a basic DFS. For level, for even level I put in A, for odd I put in B, and every time I XOR level by 1 to, it goes from 0 1 0 1 0 1. So yeah, and then I'm taking the smaller one. The reason I'm taking the smaller one is, thing is, I don't want to the last shell, right? This last range, this is not always complete, and I don't want to deal with this. And I'm back. Okay, so yeah, where was it? Yeah, we were discussing the implementation. So yeah, I didn't want to deal with this incomplete shell. What could be the case? Something like, also, not just that, take this situation. Take this situation. A star graph, a star tree, and this is the root, right? Then one value is 1, other is n minus 1. Will I be able to always get n minus 1 using these values? Not sure, because this is not filled, right? I'm not sure. That's why I'm just dealing with the smaller one, and that will always be doable because it is less than equals to n by 2. Now, so yeah, I swap it so that I have always deal with the smaller one. This is the final permutation. I store all the remaining ones. Initially everything is remaining, then I do the greedy, if the bit is not covered, then I continue. Otherwise I get the starting and ending point. Basically 5 is 101, so this is the starting bit. 2 to the power 2 is 4, so 4 to 7 values need to be inside. Yeah, so ending is st times 2. So what I'm doing is, so yeah, starting and ending, and then I am assigning in the permutation. So remember, odd had the vertex value, and I is our current vertex number. Odd is having the vertex number, and I is our vertex value we want to assign. That's what I'm assigning, removing from odd and removing from remaining. And then I iterate, and if anything is not assigned, I take one from the remaining and put it, and then I just output the value. And yeah, that